Good morning. Richard Venditti here again, and we're going to have a lecture on washing de-inking today. And we're going to describe some of the equipment and things that affect washing efficiencies. First, to start off, what is a washer? We know about laundry washers at our house, and these are similar. Let's look at our definition. It's a separation device that rinses small particulate contaminants away from fibers. So at home, we wash away oils and greases and dirts from our clothes. Here, we're going to remove small particulates, usually inks, ash, things that we don't want with the fibers, away from the fibers. A de-inking washer typically has these three steps. First, you dilute the pulp with some wash water, and of course the wash water has to be relatively clean compared to the pulp. Then you disperse the small contaminants in the water phase, because it's the water phase that you're going to separate from the fibers. And then after that, we remove the contaminant-laden water, and we get the net result is a cleaner pulp. Washers in paper recycling remove small materials like fines, fillers, inks, and dissolved species like, let's say, dissolved starch or sugars or soluble organic material. In order for washing to be successful, the intended contaminant must be small. And what we're going to find out is that there's two things that the contaminant must be relatively small versus. The first one is the opening of the wire mesh, and then the second one is the openings in the pulp filter mat that's produced typically when we do some kind of washing. Okay, in a paper mill, recycle mill, or any mill, we're going to have we have two different kinds of concepts. We've got the thickener concept and then the dilution washing. They're different in that the thickener is the purpose is to increase the consistency. Fiber mat formation is okay in this case, and thickeners are designed so that we get lower yield losses. But they're only the final result of a thickener is just to increase the consistency. It's not to do de-inking. Now, a de-inking dilution washer has a different objective. It is used to remove contaminant particles. And in order for it to do that, we have to avoid a fiber mat formation. And I'll show you why in a second. And because we're trying to remove all small particles, or the small contaminant particles, we are going to get a higher yield loss. And we're going to say that's acceptable because we've got to get rid of the ink or the other contaminants. So, okay, now this simulation kind of shows you what happens during washing. If you look here, we've got our wire mesh. Imagine that this is going to allow the dirty water to go through, and the fibers, it's going to try to trap the fibers, and that's very typical for a washing process. And what you see here is that wire mesh, the size of it, will block or not block some particles depending on their size. So if you have a particle that's smaller relative to the wire, it will pass through. If it's larger relative to the wire, it won't pass through. So the wire is a resistance to the removal of small contaminants. All right? And then the other thing that we don't think about is that that wire mesh is going to collect fibers on top of it while the water is going through it. And that wire mat, that web of fibers, as you see there, is going to act as a second resistance to the passage of those small particles. So you can see here that we've got a fiber mat here that's been deposited on this wire. It always happens during washing or thickening to more or less extent. And then you see that we have a very small particle down here, and that was able to pass through that fiber mat. But a particle this size, which should pass through the wire mesh, you would expect it to go through, is trapped because of the fibers. So you see that here's the point. The point is that we have two resistances, the fiber mat and the wire mesh. Okay? If you have thickening going on and you want to trap all your solids, you want a fiber mat. If you have de-inking washing going on, you want to avoid the fiber mat because you want to let the small ink particles go through. So what we're going to focus is we're going to look at different operations, and we're going to characterize them as either de-inking washers or thickeners. Now this next slide may be a little tough to see, but what it does is it describes different types of washing or thickening devices. So we have side hill screen, gravity decker, incline screw, horizontal screw press, belt washer, vario split. And it gives you the inlet consistencies, the outlet consistencies. But the most important thing here is this last column, pulp mat formation. You see with a side hill screen, the pulp mat formation is minimal. Okay, so that means that there's not going to be that fiber mat resistance to removing ink. And what we have here in these two columns, it shows that the ash removal theoretical, which we can calculate just based on how much water we put in, how much water we take out, 74%. The actual removal of ash, and we're using ash as a just a collect-all term for small particles, is 60%. So our actual removal, 60%, is close to our theoretical removal, which is 74%, meaning that the pulp mat's not resisting the removal of small particles. Now, let's compare that to, let's say, the horizontal screw press. Horizontal screw press takes a 4% consistency pulp and compacts it to a 28% consistency, a very thick, and it's also a very thick pad. It could be 3 to 4 inches thick. So we've got extensive pulp mat formation here, extensive pulp mat formation. And if our theoretical ash removal is pretty high, it's almost 90% because we're going from a very low consistency to a high consistency. But you see that our actual ash removal is only 35%. It's a very small fraction of the theoretical. And the reason why is because the pulp mat is trapping the small contaminants, which is great if we want high yield. It's bad if we want de-inking. So my point here is that when you look at any operation, you need to look at if the pulp mat is being formed, and if it is, that's going to have a serious impact on your washing efficiency. Okay, now the next thing I want to go over is just some types of washers. We'll look at some of the equipment, and they're broken down, they're categorized into three types, low consistency, high consistency, and intermediate washers. And we'll take a look at each one of those. Okay, now low consistency washers are characterized by a discharge consistency of about 8%. And I list 4 types of washers here, and we'll go over some of them, what they look like. Okay, a very common type of washer and very simple equipment and operational wise is what's called a side hill screen. And all it is it's a wire mesh slanted screen here. It could be wire mesh or it could be just slots in a metal foil. But basically the low consistency pulp is pumped up to the top here, and then the pulp comes down here. Now the water actually can go right through that the openings in the mesh, and the water goes through here. And what happens to the pulp is as it gets thickened, at some point you're going to lose that viscous kind of flow, and the pulp will actually ball up and roll. Okay, and that balling up and rolling exposes fresh area for washing. And so basically there's very little thick pulp mat, there's very little pulp mat here to resist de-inking washing. So this is a pretty effective way of removing ink. And then you've got your thick stock that falls down here and your dirty water that goes out the side. All right, one of the most common washing methods is the gravity decker. And with the gravity decker, this is, if you're familiar with the recovery area of a paper mill where we're trying to wash out black liquor, this is a very similar type this is the same kind of washer. So basically here we have pulp entering at 0.8% and leaving at 5%. And what happens is the pulp comes through the feed port, and the pulp goes down in this vat. Okay? And inside this vat is a cylinder that rotates in this direction. And then the rotating cylinder has a wire mesh on the outside. The dirty water actually can go through the wire mesh inside this cylinder. And the relatively cleaner pulp is deposited on the face of this wire mesh. And then we have a doctor roll here. And so basically the pulp actually is taken off this big cylinder and goes this direction. And then we have our thicker pulp right here. Now, one of the things about it is that there's a vacuum actually created. When that liquid comes into the cylinder and comes out, there's usually a drop leg. And so the fluid falling through that drop leg creates a vacuum, and that vacuum acts as an increased force to pull or push water through the wire mesh. So we're getting a vacuum to help assist us in our washing. There is a little bit of pulp mat formation, but this is a workhorse for de-inking. This shows just kind of a three-dimensional view with a cutaway. Just showing you here we have our cooch roll that takes off our pulp, and then a doctor blade that doctors it off the cooch roll, and then here's our clean pulp comes out here. And here's our white water outlet. Okay, so this would be our dirty water with our ink in it, and just shows the inside of this rotating cylinder. Okay, now we'll go to intermediate consistency washers, and so these are characterized by 8 to 15% discharge consistency. So we can get to a higher consistency than, let's say, Side Hill or a Gravity Decker. There are a few that we'll talk about next. The first one is a double nip thickener, and this device is very cleverly designed, and the design feature that's important is that it avoids a extensive mat being formed to resist de-inking washing. So how does it work? What we have is a little mini head box in here, and this head box actually puts our very thin layer of pulp right here between this rotating roll, and then we have a wire mesh that goes around like this. Okay, so there's our wire mesh. Now, what it's doing, it's a very low basis weight sheet of wet paper. Basically, it's depositing here. Now, the pulp comes in here. It gets pressed between the wire. This is going to be our first nip. It's going to be pressed between the wire and the cylinder, and then the dirty water will come out, and then the very thin basis weight sheet, wet sheet, is going to be coming around here on this wire, and then it'll go through a second nip. So that's why it's called a double nip thickener. And then more dirty water will be pressed out. The whole idea here is that if we run this belt fast enough, this wire fast enough, then we can deposit down a very thin layer of the pulp, and that way we avoid the mat. But this needs to move at very, very high speeds. Okay, the final process here is that we have a doctor blade here. It will doctor that sheet off this roll, and then it will come in here. This is a screw conveyor, and that screw conveyor will take the pulp out the side of the washer. Okay, this is a three-dimensional picture of that washer, and you can see here's the head box. It's depositing the pulp between the wire. You can see the wire here, and there's a cutaway so that we can kind of see the insides of this. The pulp comes through here, around here, then through here, and then up again, and then it's actually scraped off, and then this right here is that screw conveyor. In this case, the screw conveyor is taking the pulp out the back. And then the other thing that I should mention is that all that white, dirty water is collected at the bottom here, and it's taken out the bottom. All right, another intermediate consistency washing or thickening device is what's called a disc filter. And actually, there's not one disc, but there's many discs here. This is what a schematic of a disc filter looks like. It's kind of complicated, so let me kind of try to go through it here. If we have, let's just see. So the concept here is that there are many of these discs, okay, and they're all in parallel, and they rotate around. The discs are hollow, and they're covered by a wire mesh. And what happens is they pick up some pulp, and they pick up the pulp, and the water actually goes through the wire mesh, through the disc, and actually is collected. All these discs right here moving together, they're spinning, and the dirty water is actually collected here, okay, and then the dirty filtrate comes down this way, all right? So that's the dirty water coming through these discs. So basically the discs are rotating, and then the pulp is actually being picked up by the discs, okay? So what happens is the pulp comes in, there's the pulp and the water goes through the wire mesh, and then the pulp stays on the outside of the disc, and then the discs rotate up, and then there's a knockoff shower here, okay, and that knockoff shower is going to knock off the pulp into a chute in the middle, and then that chute in the middle right here, which we see right here, is a screw conveyor that takes the thickened pulp out. So here's the pulp discharge, okay? So the concept, rotating discs with wire meshes, the dirty water goes inside the discs, like right here, and then that water gets collected down here. The water gets collected here and comes out here. So here's some nice pictures of what's going on. This is actually the disc filter, and there are people from about here to here. So this thing might be 24 feet high. Looking in, this is the disc. So actually this is for an OCC mill, and you can see the discs right here, and they're rotating around. And on this case, you can see here's the pulp, the feed pulp, and then here are the discs moving up like this, and you can see that brown pulp collecting on the paddle, that discs, and then the water is actually going through the hollow discs and then to a collection port for the water. So the vacuum disc filter in this OCC case, because we know OCC is not de-inked, that's being used as just a thickener. There's no de-inking going on right there. We're just using that as a thickener. Now this picture right here is of a disc filter for a de-inking mill, a newsprint mill. And you can kind of get this a feeling for the size of this disc filter by looking. Here's a graduate student actually, and he's about 6 feet tall, and so you can see we've got another 12, 18, we've got about over 20 feet, maybe even more size, and the discs are right in here, so they're pretty big. And actually those discs, it's kind of hard to see, but those round discs are actually paddles that are put together. So if you can imagine a piece of a pizza pie with all the slices, those slices actually, those slices are paddles. And if we go back to this photo, here's a paddle right here. It's a little bit hard to see, but there's a whole bunch of old paddles that they've replaced. So what I'll do is I'll try and run this video. Actually, this video is not so good. I'm going to skip this video because it's not really teaching us much. We'll just see the camera shake a little bit. So we'll go on to the next one. I'll show you that one. Okay, so here what we've done is we've opened up. This is the feed material. So now you can see this is an this is ONP, old newsprint, and old magazines being recycled. Here's the feed right here. And this are our discs that are rotating. I think they're going to be rotating upwards and to the left. And we'll actually see this one in motion. So let me go ahead and start this video. Okay, what you can see here is this is the feed right here. And then we're shining a flashlight inside this disc filter. And you can see those disc filters are moving rather slowly up like this. But what they're doing is they're picking up the pulp, and you can see that that pulp is white, is somewhat white or grayish here. And the pulp's right there, and you can see that, how many are there that we can see? 1, 2, 3, 4, 5. So there's 5 of them. They're all attached to the same kind of shaft. And these bars that you see that bar right there? That's one of the, that separates the pieces of the pizza pie. So this right here, from here down to here, and we can't see the other edge of it, is one kind of slice of pie. It's piped up to that thing, and it can be disconnected separately. So that's that. See if we can get back.
You've got to do F8 twice.
I think I'm okay.
Okay.
Okay, but I need to do F8 one more time. Yes, okay, so we've got it. So that's a disc filter, and disc filters are typically used for thickening, but they can be used for washing. Intermediate washers are kind of flexible. They can go as thickeners or as deinking washers. Okay, then our next category is high consistency washers. These basically give you very high consistency discharge pulp. Two that we'll look at is the screw press and the belt press. All right, the screw press is, the name describes what it's doing actually. We take inlet pulp material, and it's at a medium consistency, probably 5% or higher. And then the pulp comes in here, and then what we have is a screw, and this screw is going to be spinning around, and it's going to be pushing the pulp up against this plate right here. And it's kind of hard to see, but right here and right here are what are called back pressure plates. They're going to offer the resistance. So that screw is going to be feeding that material up against this plate, and this plate's going to be resisting, and the pulp is going to actually get squeezed in onto this plate right here, and then finally it will be removed out here. Now at this time when the pulp is being squeezed up against this plate, we've got, again, a cylindrical wire mesh barrier, and the water, the filtrate, the dirty filtrate, will come through here, or the filtrate, and then it'll be discharged here. So we have water being squeezed actually through this cylindrical wire basket. So that's a screw press. Now, the thing to notice about this, and why this does not work well as a deinking washer, is the fact that if you look, we're going to form a pulp mat between the shafts of that screw right here and the wire mesh right here, and that distance might be 4 inches. Okay? So if you think about, if you're an ink particle and you want to travel through a pulp mat that's 4 inches thick, that pulp mat is probably going to trap you, like a very, very thick sheet of filter paper. So this is not going to work very well as a deinking washer. But it will get us to high consistencies, and those high consistencies are important for, let's say, high consistency refining, or if we're disposing of sludge, we need something like this. The next piece of equipment that I'll talk about is what's called a high consistency press. And this is somewhat hard to see, but if we take a look here, what we've got is a little head box. Okay, so we've got a head box here, and that's going to be squirting pulp in. And really what we've got is we've got 2 belts. We've got one belt right here, and they're like rubber belts. And then we've got another belt right here going down on the bottom, okay? And what happens is that pulp comes in here, and then it's going to get squeezed between rollers on this belt. So you're going to lose water off the sides, and you're going to squeeze it between these presses right here and go up like that. So what you see is that we're going to get, because we're squeezing so hard, we're going to get a higher consistency pulp mat outlet. Okay, so now that was kind of some of the equipment. Now what I want to do is just kind of talk to you about some of the variables that impact the washing. The first thing we can talk about, as we said before, was the washer wire mesh sizes. Okay, and wires are kind of measured in mesh size. So we've got 40 to 100. These are typical meshes for washers, and each mesh has a different wire diameter. And the coarser or thicker wire right here is going to do 2 things for us. It's going to give us higher open area. So if you held it up to the light and looked through it, you'd see 36% of the area is open for flow. And then the other thing is that the opening size is 0.425 millimeters. Okay? So half a millimeter, a little less than half a millimeter. And so we would expect that this kind of washer would allow things half a millimeter or less and to pass through. Let's think about that. Hardwood fiber, about 1 millimeter long. Softwood fiber, 3 millimeters long. So you can see that if a hardwood fiber is kind of slanted the right way, it's going to, or flexible, it's going to fold through and go through that. Fines, obviously, fines around 0.2 millimeters long are going to go through this thing. And then you can compare that to the finer mesh. Let's look at 100 mesh. Much thinner diameter wire, 0.1 millimeters rather than 0.25. And then the open area is a little bit smaller. And the opening size now is not almost half a millimeter. It's about 0.15 millimeters. So this is going to allow, it's going to trap more of the fibers and fines, right? Fines, but most of the fines and the small ink particles will go through. So that's the first thing we need to think about when we think about a washer. So on this graph, what we're showing here is the efficiency factor, so in a washing efficiency relative to two things, the washer discharge consistency and the particle size. Okay? Now, if we think back to that last slide, our meshes were about 0.150 millimeters to about 0.45 millimeters. Okay? Now, these different curves right here are in microns. A micron is a thousandth of a millimeter. So if we have 125 microns, we have 0.125 millimeters as a characteristic size. Okay? And what you notice is that the washing efficiency for the very small particles, like 15 microns, is around 90%, very high. But for the larger particles, like 100 microns, what we notice is that the washing efficiency is much less. It can range from 0.4 to 0, actually. So, okay, so the first thing is that smaller particles are removed with higher efficiency. The second thing we notice is that the lowest size particle is relatively independent to the washer discharge consistency. So we have a horizontal line here almost. But as those particles get bigger and bigger and bigger, what we notice is that that slope decreases more and more. So the larger particles actually are more sensitive to the washer discharge consistency. In other words, the particles that we're trying to wash out, they will, if they're bigger, there's a more likelihood that they're affected by that filter mat at the higher consistencies, and that filter mat will trap the big particles. Okay? If the particles are extremely small, like 15 microns, it's not a big deal. But if we're trying to get rid of inks that are 25, 50, 100 microns, then we're extremely sensitive to the consistency. Okay? And if you think about it, right in here is our low consistency, right in here is our intermediate consistency, and then right about here is our high consistency washer discharges. Okay? All right. Now, the other thing we talked about was that washing, dilution washing occurs because we add fresh water, we mix it all up, hopefully get the ink into the water, and then what we do is we remove the dirty water. So we can calculate what the theoretical ink removal is in one washing stage by assuming that all the ink is detached from the fibers, it all gets dispersed in the water, and all we need to know is how much of the water with the dirt or the ink in there that we take out. So this graph right here shows on our x-axis the inlet consistency in percent, and then the y-axis is the theoretical ink removal in one washing stage. So that's important. When we talk about theoretical ink removal, we're making all the assumptions that there is no fiber mat resistance, that there is all the ink is detached from the fibers, and all the ink is dispersed evenly through the wash water. So if all those assumptions are true, what we notice is that for any given inlet consistency, let's say 3.0%, as we go through these lines, okay, and these lines are outlet consistency, as we go from at an outlet consistency of 10%, we're getting a efficiency of about 72%. And then as we go to 12%, we increase that to 76. And then we go up to 16%, let's say. I should be right about here. We're getting about 84%. And then as we go up to, let's say, 40% outlet consistency, theoretically, if we remove enough water to get to that consistency, we should get to about a 96%. Okay, and this is just basically simple calculations based on those assumptions. But we know realistically that the outlet consistency of 40% is going to generate a fiber mat, and so we would expect to have a lower actual ink removed than the theoretical. So this just basically tells us that if we if we lower our inlet consistency and we increase our outlet consistency, then we will be going along this line. I mean, we'll be getting higher washing efficiency. That's the take-home message. Now, washing usually doesn't occur in just one stage for de-inking washing. It usually occurs in multiple washing stages. And so if we, this graph shows us that if we have a theoretical ink removal in one washing stage, here on the x-axis, we can get that from the curve before. And what we'll do is we'll plot the theoretical ink removal in multiple washing stages on this axis, so a system ink removal. If we have two washing stages, both with, let's say, 68% efficiency, then if we combine those two, we should get a 90% efficiency. So this curve right here is for two washing stages, and this one is for three, and 3 is very common, and then 4 washing stages and 5 washing stages. So you can see that we can combine washing stages and take one washing stage which has a low efficiency and improve its efficiency by adding different multiple washing stages. That makes sense. All right, now when we combine washing stages, we've got to be very careful because washing, as we said, dilution washing is adding a lot of water. So what we'll do is we'll use some countercurrent washing system, and we'll also reuse our water as much as we possibly can to save and conserve water, which is a big issue in paper recycling mills now. Okay, so let's take a look at this graph. What we're doing here is, here's our dirtiest pulp. Okay, so this might be, this is our pulper, this is our inlet recovered paper. And so right here is our dirtiest pulp. We've just simplified the system. We're just going to pulp it and then wash it. Typically there'd be coarse screens and cleaners here, but we're going to omit that for now. So we're going to pulp up our material, and then we're going to send it to our washer. Okay? Now that washer is going to actually, this material right here has the wash water and the pulp. Here's the wash water. It comes into the pulper. So we imagine we have low consistency pulper. Here's our low consistency pulp. And here's our number 1 washer. Here's our water filtrate. And then here's our cleaner pulp. Now that cleaner pulp will go to a second washer, and it will be washed here, and it will be cleaner as it exits. And then it will finally go to a third washer. And then finally, here's our product pulp, and it will be the cleanest of any stream in this system. So we get our cleanest pulp and our dirtiest pulp. So our pulp is flowing in this direction. Now it's called countercurrent because the filtrate actually, the wash water is actually going in the opposite direction, or the countercurrent direction. So let's just see, here's our water source, and we're going to use a clarifier as our water source. Okay, so our water source is a clarifier. And so our water will come out here, and then it will go up here. We will dilute the pulp going to the cleanest washer, dilute this pulp going to this washer, and then the filtrate, the dirtier filtrate, will come this way. Okay? So I need to mention that this right here is our cleanest water in our system. And so we're using our cleanest water to wash our cleanest pulp. That makes sense. We've got to wash with cleaner, relatively cleaner water than we have pulp. So here's our cleanest wash water, comes in here, it washes the cleanest pulp, and then it picks up some ink, and now we've got an intermediate stream right here that has ink in it. So it's a little bit dirtier. Now, we're going to take that stream and it's going to flow countercurrent to the pulp. It will come up here and it will actually be used to dilute the pulp going into the second washer. Okay. Now, once the system is stable in a steady state, this wash water is going to be cleaner than this pulp coming in here. So we're going to actually get some cleaning out of this, washing out of this. All right, they're mixed and diluted. And then here from this number 2 washer, we separate our dirty filtrate from our clean pulp. The clean pulp's going to the right. The dirty wash water is coming this way. All right, so where's that dirty wash water going? Well, it's actually going here. It's going to be used in the pulper, but it's basically being used to dilute the solids here and then being used as the wash water. So again now, here's our dirtiest pulp. It's getting washed. It's going this way. Here's one of our dirtier streams of wash water. It's going into the pulper. It's being diluted. It's diluting the solids, and it's being separated here. It's being filtered off, and then this is our dirtiest wash water stream. Okay, our very dirtiest wash water stream. Now, we can't just discharge that to the environment. That would be unacceptable. So what we'll do is we'll take the dirtiest wash water stream and we'll take it down here to what's called a clarifier. And later on in the course we'll talk about clarifiers. But basically, clarifiers are there to remove suspended solids. So the clarifier will remove suspended solids, and what I did not show here was that there's going to be a solid stream of ink and fibers and fines, and that will be discharged as sludge. And then we have our cleaner water down here, and that will be reused in the system. Now, what we do is we take some of that water and we will sewer some of that water. And one of the reasons why is because clarifiers removed suspended solids, things that are insoluble in the water. But the one thing that clarifier cannot do is it cannot remove dissolved solids. Okay, things like salts or sugars that are soluble in the wash water, dyes. These things are going to be in the wash water, but a clarifier can't remove those. So that if we don't have some discharge, we will have an accumulation of soluble material in our system, and that will eventually cause us to have poor washing of performance. So we have to have some removal of water. And the other thing that we don't show here is that if we have some removal of water and we have dry recovered paper coming in here, we have to add a little bit of water to make up for that. So that's how countercurrent washing goes. And it's very common for newsprint de-inking mills, for instance. They will use countercurrent 3-stage washing, gravity deckers to de-ink their pulp. All right, I've got one more last machine that can be considered a thickener or a washer, somewhat, mainly a thickener. That's a wet lap pulp machine. And this is just a little mini paper machine, except for the fact that we don't have a extensive drying from steam heated dryers. We don't have that. What we do here is we've got a little head box. Okay, and what this is used for is if a recycle mill is making wet lap pulp, either to ship to their own companies or to sell, they're going to try and press this material to 40 to 50% consistency because we don't want to ship around water. And the water actually causes us problems with resisting bacterial growth and things like that. So we've got a little head box here, and then we've got, we looked at this before, this is a high consistency press. We've got 2 rubber mats, okay, rolling around here, continuous rolls, and then the pulp gets in here and it gets squeezed, and the water goes out here and drains out here, and then that pulp mat, and these are kind of thick. If you ever looked at market pulp, you'll see maybe I'm guessing here about 2-3 millimeters thick, so it's pretty thick. It's not paper, and it's more than board. It's wet lap pulp. Then that wet lap pulp will come through here, and it will go through a heavy duty press. Okay, so that's going to get it up to about 50%, and then that pulp web is going to come up here, and then it's going to be cut and stacked into sheets and then wrapped up into pallets and bound. So you can also consider, this is, what I want to point out is that this is probably a lot of recycle mills might make wet lap pulp, and this is the last place where we can get water out of our pulp. And so this is the last kind of thickening method to separate water from our recycle plant from further intended uses. And that's going to conclude my lecture on washing. Just as a quick review, washing depends on two main things. One is the wire mesh is a resistance to washing, and then the second one is that the pulp mat, if we form a pulp mat, that can be a significant resistance to washing. Washing removes small particles, less than 50 microns, ink particles. It does not remove large particles, and large particles are more sensitive to the pulp mat formation. When you look at equipment, you can either categorize them as thickeners or de-inking washers, dilution washers, and we broke them down into three categories: low consistency, intermediate consistency, and high consistency. And that's a nice way of thinking about them. The higher consistency equipment with a higher consistency discharge typically have fiber mat formation or pore de-inking washers. And then the intermediate and the lower consistency equipment act as more efficient washing, de-inking washing. Thank you for your attention, and that concludes our lecture on de-inking washing.